his master's degree this semester. Patrick's a native of Madison, but secured his degree, this is a weird story, but secured his undergraduate degree in atmospheric science, maybe it's called meteorology at Lincoln, I don't know, but at the University of Nebraska-Lincoln in the spring of 2019. And then he began work in my research group that fall. And about 2 months into his tenure here, this really fantastically interesting and powerful cyclone raked the coast of California and Oregon over the Thanksgiving weekend. And Professor Morgan and I and Brett Hoover had just recently secured a grant to study type B cyclogenesis with the aim of determining how subtle changes in the initial structures that populate the pre-cyclogenetic environment impact the resulting cyclogenesis. Michael talked a little bit about that on Monday, so you maybe remember what he said. Step one, though, of executing that experimental plan was to find a robust case of cyclogenesis that appeared to involve an upper front as part of its precursor environment. And the November 2019 storm perfectly fit the bill, so we were off and running. Patrick had recently attended an NCAR workshop on the WRF model, and so we had a tool available also to simulate the storm and then do some subsequent analysis that Patrick will tell you about today. Patrick and Michael worked on the QGPV inversion portion of the resulting work, and Patrick and I tackled the QG omega portion of it. And as you'll see, the November 2019 storm was much more interesting than it first appeared, and it appeared interesting at the first glance, so it really got better and better. And this step one of our project actually evolved into a master's degree all on its own. So Patrick recently passed the department qualifying exam and so intends to continue pursuing some aspect of weather system science for a PhD, but the details of exactly what we'll pursue are not yet well understood, or we're not sure what we're going to do. But I'm happy to present Mr. Patrick Beaty this afternoon, who will describe applications of quasi-geostrophic analysis methods to investigation of a case of rapid cyclogenesis. Patrick. So I'll get the lights for you and fail
Perfect.
the right way.
Is my sound good? Does everyone hear me? Perfect. So yeah, as John said, I will be discussing quasi-geostrophic techniques.
Might be even a little loud. You're ringing a little bit.
Is that better?
Go ahead and just talk.
Hello, 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 hello.
Good?
Good?
Good.
Okay. So we will be applying quasi-geostrophic analysis techniques to this case of cyclogenesis that appeared routine, but on inspection was a lot more interesting. So this storm occurred from 25 November to 28 November in 2019. It was associated with November low pressure records, and here's an animation of the storm making landfall on the west coast of the United States. So it set November low pressure records for Medford, Oregon, and Eureka, California, as well as the all-time low pressure record for the state of California. And that was at Crescent City, which is in the far northwestern part of the state. Oops. And then off the coast, two buoys recorded record significant wave heights, which is the average of the highest waves within, highest 1/3 of the waves within a wave spectrum. And so along with setting pressure records on the United States coast, offshore, over the ocean, it also set records. And then it accomplished a 24-hour maximum central pressure deepening rate of 43 hectopascals in 24 hours between 0 UTC 26 November, 0 UTC 27 November, which included a 3-hour deepening rate of 12 hectopascal. So this is extremely strong deepening within a very short period, within a 24-hour period where the storm was explosively deepening. So we can look at a GFS reanalysis of this storm here. We'll first focus on channel A. These are sea level pressure contours with 950 moist isentropes in the green dashed contours, cold fronts and warm fronts, and then highs and lows indicated. And this highlighted X is where our storm is developing. And so it develops along a baroclinic zone associated with this low pressure system south of Alaska, but in the middle of a high pressure system. So an unusual area for development within the middle of a high pressure, which is fairly strong. It was accompanied with a baroclinic zone at 850 here, and this baroclinic zone, these are showing potential temperature contours in the red dashed, and then positive frontogenesis. And so this baroclinic zone was frontogenically active, especially on the warm side of where the storm is beginning to develop. It was associated, based on where it developed in this high pressure system, it developed right in the ridge axis of this decently strong geopotential maximum. And these are showing geopolitical height contours in the black, and then also potential temperature. And then this is at 300 hectopascal. We see a jet streak, and then again on this ridge axis here. So an unusual area for this storm to develop. So stepping 12 hours ahead now. That was the beginning of the simulation. Now we are at 0 UTC 26 November. This is the beginning of the period when the storm is had its 24-hour maximum deepening. So we see our storm beginning to develop. It is still associated with this baroclinic zone at the surface and a warm and cold front now beginning to develop. And you can see it carved directly in between this high pressure system. And so, again, an anomalous position for this storm to begin to develop. It is associated at 850 with that same baroclinic zone, which is still frontogenically active. Now we see a shortwave feature beginning to move in the vicinity of our storm. And so it is no longer under this influence of this ridge axis. It's now more under this influence of the shortwave with associated positive relative vorticity. And some semblance of a baroclinic zone at 500 hectopascal as well, as shown by the potential temperature contours. And then we can see our storm is now at 300 hectopascal in the right entrance region of this anticyclonically curved jet streak here. And so, and there's also, you can see the shortwave beginning to be observed at 300 hectopascal as well. And so step 12 hours ahead now. Our storm has deepened. It is now below 1,004 hectopascal. It has moved completely through the high pressure in which it developed and has distinct cold and warm fronts at this time. This is 12 UTC 26 November. The baroclinic zone in which it formed is still frontogenically active and now is resembling more of a thermal ridge. We can see now at 500 hectopascal a very interesting feature. So this is positive relative vorticity, and this slug of positive relative vorticity extends from North Alaska all the way down to where a storm is situated. And so you're getting incredible amounts of geostrophic relative vorticity advection, as well as PVA by the thermal wind, positive vorticity advection by the thermal wind. And if we notice, the potential temperature contours are tightly packed at this time as well. And so this is an indication that an upper front is also beginning to develop. And you can see the increase in positive relative vorticity to verify that as our shortwave moves along with the low pressure system at the surface. Now at 300 hectopascal, the jet streak has moved and transitioned to the west of where our storm is located, but it is still out ahead of a shortwave. Now our storm is at strongest. It is well below 980 hectopascal, right about to make landfall on the west coast of the United States. A well-defined cold front beginning to overtake the warm front at the surface. It's beginning to lose the thermal gradient in which it developed, and most of that frontogenical activity is due to orography over the west coast of the United States. We can see it's situated now right in the region where the positive relative vorticity is the strongest, directly in this geopotential minimum and this trough. And you can see a still very strong upper front at this time, and even situated slightly to the west of our storm. And then that same jet streak is continuing to move further to the west and not influencing our storm as much. The final analysis time here, 12 UTC 27 November. Our storm's beginning to fill. Just a cold front associated with it. It lost any resemblance of the baroclinic zone in which it formed initially. It's centered in the middle of this geopotential minimum. The upper front is well to the west of where our storm is located. Same with the jet streak. And so upon inspection, this looks like type B cyclogenesis, which is an upper level wave, which was the upper front, the shortwave feature, a jet streak moving over a lower level baroclinic zone. So it fits that build. But we can go through an analysis technique to understand why it was so strong. And also, we want to learn how it set the pressure records over the west coast of the United States and the ocean, right off the west coast of the United States. So before going into the analysis techniques, this storm is even more anomalous besides just setting pressure records and wave height records as well. So there are 3 ways in which this storm was particularly anomalous. So the first is the location of the maximum deepening here. This is a climatology of maximum deepening positions for cyclogenesis events from rover 1984. The contours are the frequencies of cyclogenesis and maximum deepening positions. We can see a maximum off the Japanese coast, south of Alaska, and then off the east coast of the United States. And so we'll plot where this storm developed. First, it formed within this region, south of Alaska, so a typical region where you expect cyclogenesis, but these are maximum deepening positions. So where the storm actually underwent its maximum deepening was right off the west coast of the United States. And if you notice, it's outside of the frequency contours. So this makes, based on this climatology, and this is a period from 1976 to 1982, this storm was outside of the frequency contours of maximum deepening positions. So this analysis is great. It is from the 1980s. So we can look at a more recent event in climatology. This is Wang and Rogers 2001. Did the same sort of technique. These contours are normalized by frequency, and there's a smoothing applied to them. But we can make up the same 3 maximum positions. This is the maximum off the Japanese coast, off Alaska, and then the east coast of the United States. And so we'll then plot where our storm underwent its maximum deepening, and it's this red star here. So also outside of the frequency contours based on this study as well. And this is a period from 1985 to 1996. So we are accumulating now about 15 years where this storm was anomalously positioned in its maximum deepening. Further, we can look at Zhang et al. In 2017 did the same study analyzing maximum deepening positions just over the northern Pacific. So more localized where this storm actually developed. So we'll focus on the Northeast Pacific panel here. And this study was over a 15-year period, 2000 to 2015. Here's where our storm underwent its maximum deepening. So the past 2 studies was outside of the frequency contours. This is on the fringe. So we can assume then that this storm was well outside of where you would typically expect maximum deepening positions. It was outside of the contours from the first 2 studies. It's on the fringe of this one. So the area in which it underwent its maximum deepening is anomalous. And it is also situated right off the west coast of the United States, which is interesting in and of itself. So then we can look at the track of the storm. This is going back to Zhang et al. 2017. Here is a plot of the cyclogenesis events for the Northeast Pacific Ocean in panel E. We can notice from panel E and all the panels, most of these storms track southwest to northeast. Some of them, even over the Northeast Pacific, track south to north, but a majority of them are going southwest to northeast. So we can plot the storm track of this storm. Here's an approximate drawing of the storm track. This tracked northwest to southeast. And so you can notice it's outside of the climatology of this storm as well. No other storms occurred where it did, but it also was 90 degrees out of phase from these other studies and other cyclogenesis events. And so based on this, the storm track was anomalous as well. And then the deepening rate of this storm we can look at. So this accomplished a deepening rate of 43 hectopascal in 24 hours with its maximum 24-hour deepening rate. It occurred at a mean latitude of about 45 degrees north. Using a definition from the original bomb cyclogenesis paper, Sanders and Giacomo, 1980, they used a calculation for bergerons. One bergeron is 24 hectopascal deepening, 24 hours, normalized by 60 degrees north. So this storm did not occur at around 60 degrees north, but using that definition, it was about double what is needed for bomb cyclogenesis. One bergeron would be associated with 24 hectopascal, 24 hours at 60 degrees north. Going back to Zhang et al. 2017, this definition now applies more towards the northern Pacific Ocean. Using a mean latitude of 45 degrees north, our storm is also about double what is needed for bomb cyclogenesis. And this, from that same study, both of these classifications rank it within the strong explosive cyclogenesis event. So we can look at then a histogram here from that same study, Zhang et al. 2017, focusing in on the Northeast Pacific Ocean here. A histogram of all the Bergeron values, one being 24 hectopascal, 24 hours. Here's where our storm was. It's on the tail of this histogram. So, despite accomplishing its maximum deepening outside of climatology, its track was out of phase from other tracks. It still was on the upper echelon of all of these cyclogenesis events. And this is one specific study, but about a 30-year period, it was outside of the what is typically expected for explosive cyclogenesis. So now we go into actual understanding of how this storm accomplished what it did. So we can first look at PV thinking. This PV thinking was resurrected by Hoskins et al. 1985. It was not the first, he was not the first paper to introduce PV thinking, but this is what is typically attributed to potential vorticity thinking. It's the idea that potential vorticity, PV, will incorporate information about circulation and stability into a single variable. So then you can associate changes in circulation as a result of changes in stability and vice versa. So you get information about the atmosphere just including one variable, PV. And then PV is also conserved for adiabatic and frictionless flow. And so it can be used as a tracer for air parcels throughout the atmosphere, as the PV will be conserved as long as you assume adiabatic and frictionless motion. We can adopt this PV thinking and calculate QGPV, one flavor of the PV derived from quasi-geostrophic assumptions. So here's our equation for the QGPV. It is the sum of the geostrophic relative vorticity, the planetary vorticity, and then includes a vertical derivative of temperature and static stability. So there's a lot of information about the zonal winds, temperature, stability within this QGPV itself. And one thing that makes it so useful, it is a linear operator. And so you can separate each of these individual terms within the PV, the QGPV, and you can calculate how much of the QGPV owes its magnitude to just geostrophic relative vorticity, and so on. And then for non-adiabatic flow, or the real atmosphere, if you notice a change in QGPV, that is either associated with frictional dissipation or diabatic heating. And so it can also be used to track where is there frictional dissipation and or diabatic heating occurring, because it should be conserved for adiabatic frictionless flow. So we take our QGPV, now we're going to invert it, and I will go through what this means. This is following Hickam et al. 1996. Here's a variation of our QGPV. I subtracted the Coriolis parameter to the left side, so now we have what I'll call Q prime here. It's a function of geostrophic relative vorticity and then the vertical derivative of static stability and temperature. So then an inversion can proceed when you have you know what the distribution of QGPV is. You need QGPV to invert QGPV. You have a knowledge of the boundary conditions, and this can be prescribed by the user. And then you have a balance condition that will relate the mass to the momentum within your inversion. This is geostrophy. We are assuming quasi-geostrophic potential vorticity, so we use geostrophy for this condition here. So how do we actually do this inversion? We apply a linear inverse operator, apply an inverse Laplacian operator, to this equation where we have Q prime here. We notice that this is a horizontal Laplacian of the geopotential. This is a vertical Laplacian of the geopotential. So we can apply an inverse Laplacian to the right side of this equation and back out what the geopotential should look like based on the distribution of QGPV. And so we solve the equation for geopotential based on distribution of QGPV. And a valid question at this time would be why? We know a model will give us geopotential. Why go through all of this necessary calculations to get geopotential if a model will spit it out? We can associate the geopotential and the geopotential anomalies with different levels of the atmosphere and different forcing in the atmosphere. So here's a schematic of the dynamic tropopause in red pressure decreasing on the y-axis here. Let's say we have this tropopause, it's going to undulate. This undulation is associated with a maximum in QGPV. So higher QGPV locally in this region here. And so based on that QGPV maximum, we can calculate anomalies of this QGPV maximum. So we can get an anomalous value of QGPV within this tropopause undulation and associate how much of this tropopause undulation and this QGPV anomaly will extend to the surface. That is how we do, that's why we do QGPV inversion. And so how we calculate this QGPV anomaly, we take the time mean of the QGPV throughout the entire spatial distribution of our model and calculate instantaneous differences from that time mean. We do this using the WRF model. So we'll use the Weather Research and Forecasting Model, or WRF. This is WRF version 4.1.4, a 60-hour run, well within the bounds of when our storm developed and strengthened. 3 hourly time steps, 33 evenly spaced vertical levels, 30-kilometer grid spacing, and this was initialized by GFS data, 0.25 degree by 0.25 degree resolution. So we have our distribution of QGPV anomalies. We apply the inversion operator.
Patrick, how did you get the anomalies in the QGPV? All you did was tell us that you ran the model. What did you do after that?
Do you mean like the time mean?
Yeah.
Yeah, so we run the model, we calculate QGPV throughout the 3D distribution, and then we take, at each time period, at each 3 hourly time period, we subtract the instantaneous QGPV from the time mean, and that gives us a distribution of QGPV anomalies.
The other way around, yeah, okay.
And so we have our QGPV anomalies here, and if we apply the inversion operator, a maximum in QGPV anomaly will be associated with a minimum in height field and height anomalies. So then we can associate this QGPV anomaly with this height field and analyze an arbitrary level in which we want to know how much is this QGPV anomaly affecting our level. And so this level is taken as 950 hectopascal. Our storm gets well below 1,000 hectopascal, but does not get below 950 hectopascal. So we will take 950 hectopascal is the location of our storm here. So we can take QGPV anomalies throughout the atmosphere, invert them, get a distribution of height fields, and see how much of the height anomaly is affecting our storm at 950 hectopascal. Then we can split up our atmosphere into 3 different levels. So we can split it up into UPERT, MPERT, and SPERT for upper perturbation, middle perturbation, surface perturbation. And we can associate then QGPV within this UPERT level. How much is the QGPV just in this level affecting our storm at 950? We can do the same thing for MPERT here and SPERT. So at this time, we would take just the values of QGPV within the UPERT level. These would be zeroed out, and we would just invert this QGPV anomaly and then see how it's affecting our storm at 950. So that is how we go through our QGPV inversion here and why it's so useful. We can relate distributions of QGPV anomalies and see how they affect the surface cyclogenesis. So this is what it looks like when you go through that inversion here. Panel A will be a full column, so we invert the entire column of the atmosphere. Panel B is the UPERT inversion, just the upper levels of the atmosphere, from 450 to 100 hectopascal. Our mid-level perturbation, panel C, 800 to 500 hectopascal. And then our surface perturbations, 850 to 950, and this includes potential temperature at 975. So, at this first time period, 12 UTC, 25 November, we notice there's a slight negative height anomaly where our storm is beginning to develop at this highlighted X. None of this is contributed from QGPV within the UPERT level. All of it is associated with MPERT and QGPV within the MPERT level here. And then there are actually positive values of the height anomalies associated with SPERT and this cool pool at 975 hectopascal. So we'll go through the same 12 hours increments This is now 0 UTC, 26 November. Our storm is beginning to develop. Associated increase in the negative height anomaly field. We can notice a negligible portion comes from UPERT. Also a negligible portion comes from MPERT. And majority of this full column height anomalies are associated with SPERT here. And so this can be attributed to QGPV within the lowest level of the atmosphere from 850 to 950, and also this potential temperature anomaly here. 12 hours later, our storm is beginning to enter its maximum 3-hour maximum deepening period. Associated increase in the height anomalies with our storm. Again, no contribution from UPERT, about 10% contribution from MPERT to the full column height anomalies, 90% from SPERT here. And this is, again, could be associated with QGPV, but also this potential temperature anomaly at 975 hectopascal. 0 UTC, 27 November. Our storm is about to make landfall. It's its strongest, has its strongest height anomalies. A negligible portion, again, from UPERT. About 1/5 of these full column height anomalies are from the MPERT level. 4/5 from SPERT. And if you see, it's beginning to be dislodged from the positive potential temperature anomaly at 975 at this time, as it moves inland. And so here's our final time. Our storm is weakening in the height field. UPERT beginning to contribute some, but still very, not as significant contribution as the other levels. About 20% from the MPERT level and the rest from SPERT. So this is against what we would expect. We have a type B cyclogenesis event. We know that there's an upper wave. We know that there's a fairly strong upper front. We would expect UPERT and MPERT to at least have some substantial contribution. However, SPERT, 950 to 850, including the potential temperature anomalies at the surface, that is what's driving height anomalies at our low pressure center location. So we spent about 15 months trying to understand why. Does this make sense? It doesn't. We would expect a different distribution, at least some contributions, significant contributions from UPERT and MPERT. We don't see that. We see SPERT is the main contributor to all of these forcings throughout its life cycle. So we can impose another perspective now as to why this might be the case. Do these results make sense? Let's see if another method of analysis fits our expectations. So that's what we'll deem the QGomega perspective here. We'll start out with the isobaric continuity equation, where omega is the total change in pressure with respect to time here. We can rewrite horizontal divergence as del dot V. We can then move del dot V to the right side of the equation and integrate with respect to pressure. So now we can relate omega at the surface pressure is the integral of the top of the atmosphere to the surface of the horizontal divergence. This will give us a rate of change, or time tendency of the surface pressure. So we can relate then QG omega to the time tendency of surface pressure. We can then expand the total derivative of the surface pressure here into the Eulerian term, the ageostrophic advection of surface pressure, and then mass flux at the surface. And so from this, we could calculate this entire expression and relate it to the total rate of change of surface pressure with respect to time. However, we're going to make an approximation. We are going to neglect the ageostrophic advection of pressure. This will most definitely lead to pressure increases where we have lower pressure and divert pressure away from higher areas of pressure. And then we'll also assume no slip conditions. And so this will get rid of the last two terms in this expression, and we can relate the total change of pressure at the surface is just the Eulerian rate of change of pressure at the surface. And so this is an approximation. I want to stress that again. We are neglecting two terms that will definitely change this value. However, we are just concerned with comparing the omega, the QG omega, to these values. We don't necessarily care what these values are, we are just comparing them. And this will make more sense as I keep going here. So then, we can plug in this Eulerian rate of change of surface pressure back into our expression here. And this is now an approximation of the Eulerian rate of change of surface pressure. There's this expression here. So then, we can integrate from 100 to 950. Our data set is limited from 100 to 1,000 hectopascal. Fitting with our QGPV inversion, we're going to limit ourselves to 950 as our lowest level in the atmosphere. And so this is our expression. We can relate then near surface pressure tendencies to QG omega. So that's why it's called the QG omega perspective. We're relating near surface pressure tendency to a distribution of QG omega. We get these values of QG omega from the Q vector form of this equation, and we can solve this expression for the Q vectors and then invert it to get a value of QG omega here. So we can take these values and this expression up at the top here. We can apply our same bounds that we did for the QG inversion, QGPV inversion. So we'll state that we have a full column QG omega is the sum of the U per QG omega, M per QG omega, S per QG omega. So this will allow us to compare different levels of the atmosphere again, and the QG omega associated in those levels, and see their relative contribution to the full column QG omega. So here are three expressions now that we are employing in this analysis, starting with this expression here for U per. This is the Eulerian rate of change in the near surface pressure tendency, which is the contribution to the 3D distribution of QG omega just in the U-PERT level, and we will integrate throughout the entire column. So we are just calculating QG omega within the U-PERT level, produces a vertical gradient, and then we integrate that vertical gradient throughout the full column to get the relative contribution of QG omega at the U-PERT level to near surface pressure tendencies. This is just by the U-PERT level. We'll do the same thing for M-PERT and S-PERT here. So these are the results of these expressions is what I'll show next. So now we are looking at the same orientation as before. We have our full column, U-PERT, M-PERT, S-PERT, and these are the contributions to near surface pressure tendencies associated with the full column QG omega, U per QG omega, and so on. So from this first time period, we notice we have a distribution of pressure rises. These are contoured in hectopascal per hour. So pressure rises behind our storm, pressure falls ahead of our storm. M-PERT and U-PERT contribute nothing to these initial pressure tendencies at the near surface. It's all confined to S-PERT here at this initial time. This is the same analysis period that I started with, 12 ETC 25 November. Stepping 12 hours ahead now, we have an increase in the pressure rises behind our storm, same distribution and same magnitude of pressure tendencies around our storm. We notice that U-PERT, there's no contribution again. M-PERT, there is slight contribution, but is well away from where our storm is located. And all of the pressure falls ahead of our storm now are again confined to just the S-PERT QG omega. Yeah?
I was just inquiring on the, I guess it's 2 slides ago, so the individual omega is related to the perturbation of the level that we're at. Is that? So
What do you mean by
on the right-hand side, there's an omega with U-PERT, that's the upper level omega?
Yes.
No.
Associated with,
No, it's the forcing in the upper perturbation layer from 100 millibars to 400 millibars. All of the del dot Q that's in that layer is then inverted to give you a 3D distribution that's based only on that forcing. That's what we call omega sub U-PERT.
and we integrate that over the entire column, not just the level?
Yeah, because you can get a 3D distribution of omega from the forcing at any layer that you want. You can partition the layers because it's linear. So the upper perturbation forcing can give you a 3D distribution of omega, and then you do the integration on the vertical derivative of that.
Okay, thank you.
So, going back to this picture, all of the forcings for near surface pressure tendency are contained within the esprit level at this time again. We'll step 12 hours ahead now. Our storm is beginning to strengthen significantly. You can notice there's more of a pressure tendency at the near surface associated with the strengthening storm. We can also notice in the pole column and then also in the U-pert a elongation of pressure rises behind our storm. This is associated with sinking along the upper front. So this is indicative of that upper front formation. We have a nice distribution of near surface pressure tendencies around our low pressure center. Some of this is captured in M-pert, but a majority of it is captured with S-pert, again, for this 12 hours now in the future. So we'll go to 0 UTC 27 November. Our storm is beginning to make landfall. We can see still a nice couplet of pressure rises behind our storm, pressure falls ahead of our storm. A majority of this is contained within the S-pert level again. Some contributions from M-pert here, negligible contributions from U-pert. A majority of it is within S-pert again. So we'll look at final time period for continuity. We can see there's a disorganized orientation of pressure tendencies, and at this time, near surface pressure falls are also associated with S-pert here. So, here is looking at now summarizing both the QGPV inversion and QG omega. We have our 5 time periods that we analyzed, the relative contributions in percents of QGPV and QG omega within U-pert level, M-pert level, and S-pert level. At this first time period, where blues indicate the QGPV inversion results, greens indicate QG omega results. First time period, we see M-pert from the QGPV inversion contributed all of the forcings for height anomalies at 950, which would be associated with cyclogenesis. The QG omega perspective identified S-pert as the main level and main contributor to forcings for cyclogenesis. At this first time period is the only period in which there's a discrepancy between the two methods. The other 4 time periods, S-pert is the main contributor by far. Some of these, and especially in the QG omega, 100% of the forcings for cyclogenesis are described by forcings within S-pert here. So now we have a clear cut. We have 2 analysis techniques that are giving us the same results. That S-pert and QGPV, QG omega within the S-pert level is the main driver for forcing the cyclogenesis event. And so to summarize, QGPV inversion, S-pert, QGPV anomalies have the most substantial influence on near surface height anomalies, which will then affect surface cyclogenesis the most. So from the QGPV inversion perspective, S-pert QGPV was the most substantial in forcing cyclogenesis. From the QG omega perspective, the contributions to near surface height falls is predominantly forced again in the S-pert level. And this will have the most influence on surface cyclogenesis. So both of these perspectives highlight S-pert as the main layer for forcing cyclogenesis within the storm, which is again not fitting the type E cyclogenesis that was initially thought. We have this nice upper wave, we have a nice upper front, jet streak. Those, from these analysis techniques, seem to be uninfluential. It seems to be all of the forcings are contained within 850 to 950, and then potential temperature at 975. And overwhelmingly so describe this cyclogenesis. So then, what is driving the cyclogenesis? We can confidently say, we know this, it's QGPV and QG omega within the S-pert level. That is what's driving cyclogenesis. Why is this the case? That is still up for question. These results are not fitting what would be expected for type B cyclogenesis. We can speculate why this is the case, but there is definitely more work needed to understand why. Is there diabatic heating effects? Is there an erosion of PV associated with a PV undulation? Is there a generation of PV near the surface associated with diabatic heating? Potentially. We don't know. is the phasing of the upper level wave and the surface cyclone such that they can't mutually amplify? That is potential reason why the upper level wave is not influential in surface cyclogenesis. Potentially, this might be the case. Is it something else? We don't know. We can very confidently say we know what is driving the cyclogenesis. Why? Up for speculation. Future work is definitely needed for this. And so with that, I would like to acknowledge, start my acknowledgements. John Martin first, for being my advisor, being flexible within a pandemic, and for always being supportive of my work and my questions. Michael Morgan and Stephanie Henderson for being a part of my committee, and for letting me TA for you both. I have learned a lot. In my time being a TA, my wife Jessica, she knows nothing about what I do during this. It's like a foreign language to her, but she still supports me throughout my entire time. I'm home inventing about some code that's not working or QGPV inversion results that don't make sense. My family, they have allowed me to go to grad school, and I'm very appreciative of all of them. Everyone listed by name and not listed by name. I have had the pleasure to interact with all of you, and I appreciate all of our conversations. And then everyone else associated with AOSS. You have all been influential in some way in this work, so I appreciate all of you. And with that, I'll take any questions. Yes.
I'm curious, have you thought anything about model spin-up time for why there's a discontinuity at the initial time step? Because I know, at least with work, there's some the vertical motion that there can be some discontinuity.
Yeah, definitely. And I think I showed that main time period, that's when our storm's developing, so it's not actually analyzed as a cyclone. And so that discrepancy is definitely notable, but it's not, the main period is during that 24-hour deepening phase. That's really insightful. So that the first and final time are sort of just included for continuity's sake. But the main results and the main vigor of these analysis are within that 24-hour period.
And even so, the comparisons between the model output omega and other, places of GFS analyses or something were pretty good. So
Yeah.
even at that initial time.
Yes, I can show
So
that.
they weren't so bad.
Yeah, so the red is the WRF simulation, the blue is the GFS analysis, so they still matched up fairly well, even at this initial spin-up time.
And that's 950 geopotential height, I think, right?
Yes,
Yeah.
yep, this is 950 geopotential heights. Yeah, no.
Well, three questions. First one, have you considered doing the similar method on normal cyclogenesis? See how these upper and middle level perturbation attributes the surface pressure lowering?
I think we could. There have been extensive studies involving that, so it would definitely be insightful, but this case is interesting because of how anomalous it is, so definitely could do that, yeah.
The second one is when you are inverting your QGPV, you included the surface temperature, surface data in your inversion. And I know you would also have top temperature for your inversion as a boundary condition. But does that consider the actual temperature anomaly at the dynamic tropopause or whatever the upper tropopause temperature into your upper level perturbation?
I have done that simulation. It does not change the results.
Okay.
The proportions are still the same of the results. It just changes the actual values of the height anomalies. Yeah.
And the third one is, how do you quantify, if there is mutual intensification included in this, involved in this, how do you quantify your upper level anomalies contributing to your lower level anomalies?
Are you saying if there's...
If there's mutual intensification,
Yeah.
how do you quantify your contribution of your upper level PV to intensify your lower level PV and that contribution to your surface pressure dropping?
Yeah, that would most likely be from Hoskins et al., 1985, where you can impose the circulation from the upper level QGPV anomaly onto the surface, or 950 in this case,
Yeah.
and analyze. So that would be directly from the height anomalies that we would gain from this inversion technique. Is that,
No,
am I
so
answering that question?
I guess what I'm trying to say is your surface, lower level QG increase is partly due to you have some upper level QG,
Mhm.
right? And how do you put that part of the intensification and contribute that to your upper level QG?
I guess I've tried to do that. We started doing that, but I haven't gone through enough analysis of that. That would probably be a next step. for
Well, we
sure.
calculated the advection of the low-level PV by the upper-level induced winds,
Yeah,
and vice versa.
Right.
And there wasn't very much communication between the layers.
that's right.
The top layer and the low layer. And that still remains to be one of the questions. How come? In this case, that wasn't really very strong communication.
Right.
So at least the mutual implication part is pretty weak in this storm, even though the storm's incredibly intense. So
That's right, yeah. Yes.
Your QG omega diagnostics, even in the lowest level, look mostly like just translation of the storm, you know, positive in the a downwind or negative. So it doesn't seem like that really was able to diagnose intensification. And I'm wondering, you know, you acknowledge that you're ignoring ageostrophic advection. Could you look at the derived winds that you've gotten and the model winds to look for ageostrophic contributions that might also explain some of this disagreement with what your expectations were?
Definitely. And with that analysis, I'll go back to it. I'm not saying that these results are contributing to intensification. I'm just saying for cyclogenesis, this would be a translation effect of the storm moving into this region of surface pressure tendencies. And this is identifying what is doing that. So for, in this case, and throughout this entire analysis, the S-PERT, QGPV, or QG omega anomalies are contributing to that movement. And so yes, you could definitely take then model outputted winds and calculate the actual full total derivative of the surface pressure tendencies and rerun this whole thing. However, just comparing these two is sufficient for this case because we are not trying to say that there was 8 hectopascal deepening or rising in pressure at this time in this location. We're just trying to compare the relative magnitudes of the near surface pressure tendencies. Yes?
First, thanks for your talk, Patrick. I really enjoyed it. From a non-dynamicist kind of viewpoint, I have a clarification question for
Sure.
you. When you talk about your QGPV omega method, you mentioned that you're using a barotropic assumption for the continuity equation. And earlier you mentioned that there was a clinic kind of signature, so I was wondering how you can use the barotropic equation here when you have baroclinic things present. I don't know if that makes sense.
I'm not, these are both, well, this analysis technique is not saying anything about barotropic or baroclinic at this
Oh.
time. This is just isobaric.
Oh,
Pressure
okay. I just had that mixed up. Thanks.
Yeah, that's okay. So just using the derivative of omega with respect to pressure as opposed to vertical motion with respect to height.
Thank you, Patrick.
Yep.
A couple of comments from the YouTube stream basically saying nice job. Your family is watching from a number of different states. Question from your mother.
Oh boy.
you better get this one right.
Yeah.
She says, impressive research. Simple question. Why is this finding important in the field of meteorology?
Yeah, so this is important because this is outside of what we would expect. This is a type B cyclogenesis event. As John pointed out, we are trying to look at type B cyclogenesis events and see how upper level features interact within them. And in this case, this is highlighting that that might not always be the case. There's clear signature that this is type B cyclogenesis. However, from these two analysis techniques, it seems like they are relatively unimportant, and surface forcings within the lowest levels of the atmosphere are completely driving these events, as opposed to what would be expected. You would see some contribution from the upper levels as well. And comparatively, contributions from the upper levels and the lower levels in these cyclogenesis events.
Yeah, and I'll follow on that, because that's a good answer to that. Michael and Brett are able to engineer different initial conditions that are likely to impact how intense the storm gets in an alternative simulation that employs those altered initial conditions. We had hoped that those initial conditions might be applied near the tropopause within the jet location and kind of tied to upper fronts. Your results of, as you said, headbanging against the wall for a long time trying to figure out what this meant suggests that no matter what we do to the tropopause level perturbation, we may not see much effect at all. And that seems to be completely in contradiction to things that we've anticipated and that we've seen before, and thereby drew that anticipation from. So
Exactly.
we don't know.
Yeah.
It's really interesting. There's still more to do.
Go, Ian.
I think this goes off what John was just saying, but the omega you're using is the Q vector form, correct? So that representing the full forcing.
Yes.
Have you compared that to the traditional omega equation, or perhaps the Suburb development form? I guess what I'm asking is, are the upper level forcings still there? If I look at Q vectors at 400, 300 millibars, do I see ascent, or is this confined to the lower troposphere and thus perhaps a diabatic heating impact? Can you compare those two forms?
Not specifically, but there are still strong, what am I trying to say? The upper levels are still very important. It's just that they don't extend to the surface in this case. From the QGPV inversion results, the highest height anomalies are from those upper level PV anomalies, but they just don't extend to the surface. So that's what's interesting, is why don't they extend all the way to the surface? You can definitely, there are still attributable processes going on from the upper levels. It's not that there's nothing going on. It's just they're not translating down to the surface.
Is the translation, I guess, the individual components of omega, do you incorporate the stratification directly into that, or do you calculate the forcing and then stratification plays on later? That would, because the stratification, even to the PV perspective, would impact the depth at which the PV anomaly fell.
Right. Yeah. Stratification is incorporated within the QG omega by the static stability, and then also there's a term in the QGPV version that also has static stability. So it is incorporated, and it's just a question of why. Why is the stratification such that these features don't translate down to the surface? And is that Terry?
Oh, yeah. So I thought it was interesting how you said that there were really high wave heights over the
Yes.
ocean, which I think would mean that there would be some really high wind speeds. So I was wondering
Yes.
if you can kind of describe to me the role that, specifically the role that near surface static instability plays in the progression through this storm.
Yes, that is a great point. I will go through here. There's an interesting aspect that I did not include of this storm. So yes, there were significant wave heights. This storm deepened its most significant amount and moved over a region which is influenced by coastal upwelling. And so this coastal upwelling would actually increase static stability near surface and should, in other cases, result in weakening the observed storm because of increased static stability. However, it deepens, it seems to not care. It just deepens right over these regions, still significantly right next to the west coast of the United States. And that did produce hurricane force winds over the west coast of the United States. And this occurred, this made landfall right during Thanksgiving. So there's a lot of travel disruptions as well. I'm not sure about specifically shipping and marine industry, but there was a lot of travel disruptions from this one.
Heavy snows in the mountains.
Yeah, very heavy
Really
snow.
heavy snow. Brianna.
So I know that you were specifically concerned about the development of this cyclone, but do you have any insights on what could have possibly caused the destruction of the cyclone? Or is that kind of not any contribution to this particular case study?
I think it's definitely, you need to understand what led to its destruction. The jet streak in the upper front were well away from the storm as it moved inland, and also you're going from a frictionless surface of the ocean to very high terrain. So that probably definitely played a role in its weakening, and then you also lose the upper level forcings as well. So that is another key and another nod to the upper level forcings definitely influence cyclogenesis. It's just, why was that not identified through these two analysis techniques? Yeah, Zoe?
Two thoughts. One is for this comment, or Ian's. 33 evenly spaced vertical levels is relatively shallow, or few vertical levels, especially when you're thinking about the boundary layer, and you probably only have 1 or 2 vertical levels. This is just a comment that I've been given. I'm assuming the setup is partially due to adjuvant sensitivities that'll eventually be found on this. So that's just a thought I had. My original question was, how anomalous was, obviously the storm is anomalous, how anomalous was the additional environment that was in the high pressure system that it cut through? How anomalous was the environment before the storm, and then did the storm's development change anything about how anomalous the environment was afterwards?
Yeah, that's a good question. I'll go back to those synoptic overview plots here. So the storm initially, sea surface temperatures were not any anomalous. They were pretty close to average around this entire region. It is anomalous that this decently strong high pressure system is right where the storm developed and moved directly through. It developed along a baroclinic zone, which is fairly typical with a baroclinic zone at the surface, upper level wave moving over that baroclinic zone. But to develop directly in the middle of this high pressure system is definitely anomalous, and it moves, it cuts right in between this. So aside from all of the other forcings that seem to allow this storm to maybe not be as strong as would be expected, it's just moving straight through this high pressure system. It cuts directly in between, and then if you notice as it goes through this high pressure system, relatively unchanged, it's just this surface pressure. That's the anomalous feature. So it doesn't really change the overall, besides developing a upper level trough, it doesn't really change the features too much. Definitely is impactful, but as it moves through this high pressure just remains there. And same with this low pressure system that was initially just sitting about the same region. So it seems like everything remains unchanged except this storm cuts right through the existing patterns and produces such significant impacts to the West Coast.
And there's a major development in the Bering Sea.
Yeah, I didn't even touch on this.
And the ridge building that goes on at 500 millibars is dramatic over western Alaska.
Yeah.
And that is what spurs the upper front development. Because
Exactly.
originally there's just a little wave, and then right there's this tremendous upper front on the eastern side of that ridge that develops over the Aleutians and into central Alaska.
Right.
And that's all, I think, because of the ridge building associated with that extreme development in the Bering Sea.
Definitely.
So there's
yeah.
really, you're right, there's really only 2 moving parts in this whole thing over that vast area, and they're both cyclones.
Right. Yeah, Joe.
You said the track was anomalous, going in different directions than you would expect, or than other ones in the past. Do you think that's tied to your anomalous finding that most of the forcings were in the lower atmosphere, or do you think it's not really?
Yeah, potentially. This baroclinic zone in which it formed is oriented mostly where the storm tracks. That's a good question.
Well, they tend to move in the direction of the thermal wind, right?
Right.
And that's from Sutcliffe 1939. So
Right.
if you've got a more or less zonally oriented baroclinic zone in the layer of the atmosphere that seems to be driving the cyclogenesis, that is the lower layer, that's mostly east-west.
Right.
I'm not answering why, I'm just saying these are at
Yeah,
least
yeah.
consistent.
Yeah. So it's consistent with what is presented, but it definitely was outside of the climatology of these events.
Yeah, it's just, everything about this storm is weird.
Yes, Steph?
I just have a quick question. So you mentioned that sea surface temperatures were fairly average. Was that also the case along the coast where the deepening happened?
Yep.
And when the deepening happened?
Yeah, from what I've been able to find, there was really no change in the sea surface temperatures, and they were all about what is climatological average throughout this entire period. Yeah, which is interesting. You would expect this storm, as deep and as strong as it was, to impact the marine surface in some way, but it seems like it doesn't as well.
You know, Alicia Bentley did a study of a storm from early November of, I forget what year it was, maybe in the late 90s, that developed roughly in the same spot, and it had, the satellite presented an eye. It looked like an extratropical hurricane. And so there's something peculiar about that spot. I don't remember the other details about that development, but she wrote a fine paper on that. This thing looks extratropical. The one that she talked about looked tropical, and it even had a PV tower in the middle. Just, I have that on a poster outside my office because we looked at that storm. Me and Mike Fries looked at that. So there's something funny that goes on there at this time of year, even in spite of really warm surface, cold surface temperatures in the ocean.
Right.
All right, it's 1:03, so let's give them a minute.